Hi, my name is Walter Alexander Nahra, and I'm a student at California State University, Los Angeles, and these are my notes for week 4 of CS 4540. Now, last week we took a brief overview of what transformers are, who created them, and general ideas about them. Now, for this week, we're going to go a little bit in depth into what transformers are and explain a little bit more in detail. So you might be wondering why transformers are so important. Well, you heard of the term GPT. It's used in names such as ChatGPT. Well, it stands for Generative Pre-trained Transformers. Generative, in this case, means models generates new text. Pre-trained means that the model was trained on large amounts of data, and transformers are a special kind of neural network, uh, aka a machine learning model. Transformers are crucial aspects of the model and are the contributing factor for the recent boom in AI. Now, transformers are also used in other areas besides um, chatbots. They include things like voice to text, which converts human speech into text to voice, which is outputting audible speech from text to image, which generates a visual image based on text descriptions, and machine translation, which utilizes mathematical models of data to facilitate learning in computers without direct involvement. Now, transformers are very complex in nature. To give an example of how complex they are, the simplest form of machine learning might are are what we consider linear regression, where inputs and outputs are single numbers with the goal of finding the best fit through the data. And the line is determined by two parameters, the slope and y-intercept, which are tuned to most closely match the data. As we can see in the image right here, we have our output, we have the square footage, and we see the w- that the y intercepts at a point higher than zero, and then it's taking the average between all these many different points on the graph to make a slope out, the most average slope out of them. Now, deep learning, which is what we've been discussing, is a subfield of machine learning, focusing on specific categories of models known as neural networks. They're dramatically more complicated than simple and linear regression as they contain millions of parameters. But keep in mind that a huge number of parameters does not guarantee that it will perform better as these sort of models, risk being either completely or intractable to train, prone to overfitting, or both. When it comes to these sorts of models, they must adhere to a specific format. The input to the model must be formatted as an array of real numbers. It could simply mean a list of numbers in a 2D array, or often higher dimensional arrays or tensor. Furthermore, input data is progressively transformed into many different layers, always structured like some array of numbers until it reaches the final layer as the output. Data being processed could only interact with the model parameters, aka weights, and preventing the entire model from being linear, there will typically also be some nonlinear functions sprinkled in between these matrix vector products, which we will be discussed a little bit later on into the video. As I mentioned earlier, the last week's video had a brief explanation of what transformers are, but here we're gonna go into detail of how a user input operates and goes through the transformers. Inputs are broken into small chunks known as tokens. Each of these tokens are then associated with a vector. Encoded vectors then pass through what is called an intension block, where they communicate with each other to update their values based on text. Now, attention in this case is a technique that allows models to focus on specific parts of the input sequence when producing each element of the output sequence. Attention blocks are responsible for figuring out which words in the context are relevant to updating the meaning of other words and how exactly those meanings should be updated. The vectors are then passed through a multi-layer perceptron or feed-forward layer where the vectors don't talk to each other and they all go through the same operation in parallel. Um, in a multi-layer perceptron are a single layer of neurons where information flows only in one direction from the previous layer to the next without any loops or connection back to an earlier layer. Hence why they're also referred to as a feed-forward layer, as they're feeding the information from one layer to the next with no communication or method to go back to the previous layer. There are a series of layers alternating between the attention blocks and multi-layer perceptrons. The vector passes through until all the information necessary to predict the next word is encoded into the last vector of the sequence, going through one final computation to produce a probability distribution over all the possible chunks of text that might come next. Now, I mentioned earlier that we needed nonlinear functions in order to prevent these sorts of models to become linear, which in this case includes a probability distribution. Now, the idea is that if we want a sequence of numbers to serve as a probability distribution, say a distribution over all possible next words, all the values should be between 0 and 1 until all add up to be 1. However, in practice, the outputs we get by default won't fit by this idea, as those values are often negative or sometimes greater than 1. And this is where softmax comes into play. Softmax is a mathematical function that converts a vector of numbers into a probability distribution. It works by raising e to the power of each number, giving a bunch of positive values. Then take the sum of all of these new terms and divide each term by that sum, which normalizes it into a list that adds up to 1. Instead of simply pulling out the biggest value, it produces a distribution that gives weight to all the relative large values commensurate with how large they are. With the overview out of the way, we can talk more in depth into what each process uh, means when it comes to understanding what a transformer does. Now, the first matrix of the transformer, known as the embedding matrix, will have one column for each word on its list, where said columns determine what vector each word turns into within the first step. It's labeled as WE. The upside down arrowhead refers to the E being small with which isn't very easy to translate into text. Turning words into vectors was a common practice of machine learning long before transformers, often called embedding the word. Uh, Now, the reason why we need to do this is because machine learning models don't understand actual text as they're more familiar with numbers, meaning text must be represented as if there were numbers. Furthermore, words such as bank or log, for example, have different meaning depending on their usage in one speech. Some Something these models wouldn't be capable of picking up without utilizing numbers to represent different meaning. One method that could be utilized in this sense is by asking a series of questions that could help with determining their meaning. These vectors could be visualized geometrically as points or directions in some space. A 3D slice through the very high dimensional space, projecting word vectors onto that and displaying the results. An important element to keep in mind is how, as the model tweaks and tunes its weights to decide how exactly words get embedded as vectors during training, it tends to settle on a set of embeddings where directions in this space have meaning. So as you can see on the first minute on top, uh, we have we have vectors representing man, woman, king, queen, and notice how king, king, and in this case man are higher up in the coordinates than queen and e, which signals their how much value the models put with these words, which also highlights how the models can use these coordinates in order to encode things such as gender and roles. Now, dot products of two vectors can be thought of as measuring how well they align. Computationally, dot products involve multiplying all aligned components and adding the results. Geometrically, the dot product is positive when the vectors point in a similar direction, zero if they're perpendicular, and negative when they point in opposite directions. The network can only look at a fixed number of vectors at a time, known as its context size, limits how much text the transformer can incorporate to make its prediction of the next word. So if we can look at the second image down here, as you can see in the image here, we can use dot products to with our vectors in order to push it to the desired word that we want and its meaning. So we have cats with plural and then just regular cat, and notice how the cat is being pushed towards the direction of cats. Now we'll be skipping over the intention block and jumping towards the end. Don't worry, next week we'll be discussing more in detail attention blocks and the procedure when it comes to that section of within a transformer. But for now, let's jump. Let's continue towards what happens towards the end of the transformation. Now, the desired outcome is the probability distribution over all possible chunks of text that might come next. The process involves two steps. Using our matrix that maps the very last vector in the context to a list of, let's say, roughly 50,000 values, one for each token in the vocabulary. There's a function that normalizes this into a probability distribution, which is softmax, which we had discussed earlier in the video. And then embedding matrix refers to how the training process turns out to be much more efficient if we use each vector in this final layer to simultaneously make a prediction for what comes immediately after it, aka predicting the next word in the that the system prints out, which is labeled as WU, which again is written this way just because it's hard to write it down in a document. And finally, these are the videos we saw during the lecture. As always, we had 3Blue1Brown's video on transformers. We also have Code Basics video, which goes over the same type of information that 3Blue1Brown did. Notice how we have a time step between 150 to 23, 28, since in Code Basic video is not only longer, but also goes into detail with attention blocks, which again will be discussed next week. Thank you for watching my video, and I hope you have a good day.